Actually, okay.
Sorry.
I have to say that I am not from the community of, say, computational statistics or probability community. No, I come from the community, say, specialized in numerical analysis and modeling. And the point is that, so 5 years ago, when I started to work in that, we decided with a group of colleagues to look at these methods to see if it can bring things and new things and fresh air to what we were doing in the modeling, classical modeling of PD. And actually, but then I use for certain type of problem, I use stochastic gradient descent, and it was for me extremely difficult to understand the method. The reason is that, coming from my perspective, the notion of convergence of the numerical method, the notion of the accuracy that you can get, is something extremely important, and we really wanted to understand stochastic gradient descent with respect to this perspective, but not the classical way. I mean, the way these methods were designed. This is why I will report on some what I call NN function. It is some function that you can code exactly. I will explain why exactly in neural network structures with ReLU, so that we can try to, and because it is exact, I will explain how it is exact. We can benchmark the stochastic gradient descent methods to check if they are accurate or not. And so it means, when I say we benchmark, it means that we try to get an accuracy 10 to the minus 2, 10 to the minus 3, 10 to the minus 4, blah, 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 and it continues to go down. Any accuracy. Of course, perhaps this objective is childish a little with respect to what are the real objectives of stochastic methods. But nevertheless, it is the research that I have done these years, and this is what I will report on. Okay, so it is an academic question. I will explain now. For certain okay, excuse me. Okay, so I have 3 parts on my talk. In my talk, the general introduction, which is the classical stuff, or classical and less classical stuff. And then, as you will see, these functions that are captured by neural network structures with ReLU are polynomials, actually. In this case, they are polynomials. But exactly. And actually, the whole point will be to understand the structure of some series, mathematical series, converging series that gives you these polynomials on neural network, and how it helps to reformulate gradient descent methods in a way that I will explain, so that I can get almost exact, asymptotic accuracy, but for a very academic problem. And then perhaps, if I have time, I will report on other problems for solving other PDs and different projects. Okay, so the introduction. So the framework of this research is the classical one, where we have a data set, and this data set, there are inputs called xi and output called yi, and we have a transfer function and f or f objective. Sometimes I call it h or capital H. It is the same. It is the same function. And the point is that there is this transfer function, and we try to reproduce in the computer this transfer function between the inputs and the outputs. It means that the equation that we try to solve somehow is yi equal h of xi plus a certain level of noise. And but in my talk, I do not talk about noise. As you say. Okay, so I am completely a deterministic guy. Okay, so my gradient descent. Okay, so the size of the inputs can be arbitrary, m, and the size of the output can be also arbitrary, capital N. And this is the starting of the story. And then what people do, they model a transfer function here. It is a very naive affine function, and they assemble a cost function, which is here the least square method. I hope you see it, Jay. Can you tell me if my explanation okay? If you hear me correctly,
yes,
okay?
yes, you can see perfectly.
Okay. Thank you, perfect. And we have to minimize with the computer. So in this case, of course, it is immediate because it is the square method, and this is the training. Okay. So well, for real application, it's not exactly least square method. I mean, but more the cross entropy or the feedback divergence, meaning that we work with probabilities which are more prone to encode the type of a function. So actually, it was funny. It was for me. It was during the COVID that I was in my garden and I asked to a certain app that I have on my cell phone to recognize the type of vegetable, and it was able to get it correctly. Okay, anyhow. So we have to do the training, and this is where the stochastic gradient descent methods are used. But what is the type of function? The type of function that I use are the ones that almost everyone now recognize are the central ones in machine learning. It is that the function. So before there was the input and there was the output, and in between there was just one affine transformation. But no, now you have a certain level of, we call it hidden layers. You see, so you have the input, you have two hidden layers here, you have the output. So the flow chart, you have to read from the left to the right. Okay, so from the left to the right, and all these lines means that they are the certain coefficient of a certain transfer matrix. So the transfer matrix is the matrix of the weight W, and since it is an affine function, you can have a bias B. So it is a transformation from a space where you have a certain number of degrees of freedom. Say here it is 5, and here it is 3. It means that in between you have a matrix 3, 5 with 15 degrees of freedom. So why call it weight W and B? Honestly, it is because it is the notations of the software TensorFlow that I use where these structures are encoded. So the depth is the number of layers in the neural network structure, and the width depends. You have two hidden layers completely, and the width is 5. Okay, but of course here it is still completely an affine. A compact transformation is still an affine transformation, so there's no improvement in the mathematical structure. So the main idea is to break the. This is how I understand, is to introduce whatever tool you can of you have at your disposal, so that you break this linear structure. And in practice, it is what is called an activation function. So it means it is a nonlinear function. Traditionally, people use sigmoidal function in black, like an arctangent and this kind of thing. But more and more people use ReLU. So ReLU is actually the ReLU function, capital R, is the maximum of 0 and x. It is in red. And all my talk will be about ReLU. Okay. The point is that now people use ReLU more and more instead of sigmoidal functions. When I say people, I mean both in the engineering community, I mean at Google, for example, or in the academia. And there are a whole set of interesting theoretical questions about ReLU, and it will be central in my talk. So you can use, instead of ReLU, you have some other ReLU-like function, like the ReLU with threshold that I write T, capital T, in blue. It is like a ReLU, but it is intermediate between ReLU and sigmoidal. Okay, so these activation functions are defined from R to R, and you can activate them on a vector. So it means it is composite-wise activation. So now the class of function that we will manipulate has the following structure. You use all these affine transformation, and in sandwich between the two affine transformation, you use an activation function. So for example, if I use the ReLU function, so FR is for an affine transformation, you compose with ReLU component-wise, and then you use many of these guys. At the end, you use only an affine transformation. Why only an affine transformation? It's not mandatory, but it's standard because, of course, for example, if the objective function you want to get some negative numbers, then of course you function at the end. Okay, anyhow, it is the structure of function that people use. Okay, so this is the kind of thing that I will use. Okay, so now interesting things begin. It has been remarked it was when was it? 6 years ago by Jarodsky. I will show the Jarodsky theorem. That there is a construction, actually an interesting construction. So let's have a look at this red curve. The red curve is the hat function in finite elements method for the approximation of PDEs, but okay. So let's call it J. J, you can assemble J in with two ReLU functions. J is 2 ReLU of x minus 4 ReLU of x minus 1/2. You can check in interval 0, 1. In the interval 0, 1. And because you can compose functions, the composition of function is allowed. Let's call it J1 equal J, and then J2 is J composed with J, J is J composed with J2, J4 is J composed with J3, and so on and so forth. And you get all the functions that are drawn here. The first one, J, is in red, and the second one is blue. And you see that they oscillate more and more. They have a certain number of properties. Actually, the derivatives are orthonormal. Actually, these functions the derivatives are just members of the R basis, but okay. But an interesting thing is that it has been this function, they're connected to what has been proposed one century ago by Takagi. And actually, it was the construction of a continuous function without derivative. It was an elaboration of theorem by Weierstrass, and it is this series. So you see, you have this infinite series below, the sum over all R of 1 divided by 2 to the power R, J sub R of X, and you assemble the series. It is clearly converging because all the J are between 0 and 1, and you have the Takagi function. And you can check immediately that it is not differentiable. I will draw the function later. And okay, but actually, it is not exactly, even if it has major interest, but it is not exactly the Takagi function which is interesting in neural network. It is, you just change the weight in the series. This is what I said when I said a function which has an exact representation in neural network. It is, for example, X square has an exact representation in a neural network, provided you use infinite number of layers. This is what is written here, sum over all R. But the point is that, okay, so you have to prove that, we will prove it. You have to prove that, but the whole point, and why it is very important for neural network, is the following fact. If you truncate this series at rank P, because this is a fast converging series, you have an error that we can all calculate, which is 1 divided by 3 to the power, by 1 divided by 3 times 4 to the power p. But the whole point is that you can implement this series immediately in a neural network, immediately in a neural network that has this structure, okay? So you use 3 neurons per layer. Why 3? Because 2 neurons are used to calculate the composition, J1, J2, blah, 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 blah. And 1 extra layer, neuron, actually the line below is called the collection channel in the paper by Debussy, Devor, Foucault, and Al. It comes from electrical engineering to calculate the sum, because it is also a linear function, by linear composition, you have a sum. So the point is the following. Now you have a function, you know exactly how to calculate some weights, such that in this very simple neural network structure, so you can also implement, okay, I done that, of course. And the accuracy is this one, 1 O of 4 to the power p, but for a cost which is proportional to the number of layers. So it means that p is the log of epsilon. So it is absolutely an extremely nice formula, because it explains that if you're able to know exactly the weights, the coefficients, then you have an extremely, you have a sharp accuracy for small cost. Okay, and actually this formula, I will not explain why, is the basis of a theorem proved by Jarodsky 6 years ago, which is the following, which is, it is called best approximation theorem in approximation theory, which is take a certain class of functions which are regular in this case. All the functions have derivative in L infinity up to derivative the number n, and there exists, okay, fix a certain all these parameters. Then there exists, okay, okay, actually the neural network previously shown for the function x square, you can extend by duplication, and then you can do similar things for x3, for x4, for xy, and this is the reason why it is possible to write such a theorem, but on the basis that of the formula that was shown before, which is able to express, I mean, to approximate any function with error r with a certain number of layers, which is log of 1 divided by epsilon, and a certain number of computational units, it means neurons per layer, which is 1 divided by epsilon to the power d divided by n. So it means that if n is large, meaning that you are very smooth, then this guy is becoming smaller and smaller. But unfortunately, you also see the curse, what is called the curse of dimension. It is the fact that if you are in high dimension, it is more and more difficult to have good approximation, or you have to pay more and more. And now this result is the basis of a lot of results in numerical analysis of neural network by Debussy, Devor, Foucault, and Petrova. I already mentioned that. Peterson, Schwab, Offshore, and He Zhang, and others that I forgot. So this, okay, this is I take the liberty to advertise my master classroom notes. Okay, but anyway. Okay, but this is the theory. The problem is the training. The problem is the training. So these formulas are super nice, okay, but because, okay, for a certain number of reasons. First reasons, there is this notion of a series that approximate exactly, almost exactly, but with sharp, with fast convergence that's perfect, certain function x squared, and also you have general error function. But it is not how it works in practice. In practice, people, they do not know the coefficients, the 1 divided by 4 to the power r and this kind of things. So we have to train. So we train with a stochastic gradient method, meaning that we assemble the cost function written here, with this function f, where all the parameters, all the weights and all the biases are stored in one W, in one notation. Okay, and then you minimize with respect to weight to W, and I use a sum. So you see that exactly that I am not. Okay. I am more deterministic guy. I use always a sum notation. I do not use probabilistic formulation of that, but it is the same, of course. Okay, but the point is that J, the cost function is generally far to be convex, is highly non-convex. And the point is that where I use, so this is a report of a calculation that I made, and I made tons of this calculation, and I have colleagues that did the same. If I use stochastic gradient methods for the recovery of the coefficient, for the approximation of this function on this structure, and why this structure? Because for this structure, I know that there is the formula shown before, then it does not work at all. Meaning, if x squared is the orange curve, and so a stochastic gradient method, it is an iterative algorithm. So I have to initialize the algorithm, and here I use the stupid, the naive initialization. All the coefficients are set to 0. So all these guys are set to 0. So it means that at first iteration, it is normal. The function which is calculated is 0. I use ReLU, always ReLU. And then I let the stochastic gradient methods do the convergence. And what I see is that only the exterior bias is able to be approximated, and all other coefficients are stationary. It is a well-known fact in machine learning that there are some these cases of degeneracy, and this is exactly one of these. So it just means that here, in this case, stochastic gradient descent doesn't work. So for me, it was really a paradox, you see, because I have a formula, I have an exact representation, which is nice. I know that there is the possibility that some weights, not the possibility, that there exist weights and biases, so that on this structure, I get x squared up to a certain very small accuracy, but stochastic gradient descent is not able to get it. So then I decided to use this kind of functions to benchmark stochastic gradient descent and to try to see if there could be situations where I am able to make this SGD method converge to the exact solution. I do not comment on this, but it is the same problem. It is the same problem. Oh, yes, let me comment. This is the accuracy. So it is the same experiment, but instead of the naive initialization, I use as advertised random initialization. So now it is possible to converge. So on axis, it is the number of layers, and on the vertical axis, it is the error between the orange curves and the function which is constructed. And what you get something that starts to converge, but like 1 divided by 4 to the power 2. In any case, never the theoretical estimate. Okay, and after a certain number of layers, it just blows up. So I do not show what's going on after, but we lose. Okay, so most of my talk. So I wanted to do some calculations for this presentation with non-smooth function, and okay, unfortunately I had a problem with my computer, so yeah, it was not possible. But nevertheless, let us go back to the Takagi function. What is interesting with this Takagi function is that it is so it is this function where the weights are 1 divided by 2 to the power r, and it is drawn here. Okay, so it is a function which is nowhere differentiable. You can prove that. Actually, it is simpler, but nowhere differentiable. There are many ways to be non-differentiable at a point, but you can calculate the BV semi-norm of. Actually, this function is not BV. It's not BV. You can check. And the point is that with exactly the same structure of functions, you can get at the same time the function x squared, but also this function. You just have to change the weight. And it is an explanation. It is very simple, but nevertheless, it is a very interesting explanation why this neural network structure are able to capture, a priori, if everything goes well, at the same time, very irregular function like this one, and very smooth function like x squared. So what is this picture, this funny picture? Is that this, actually the Takagi function has another nickname, is also nicknamed the curve, the blanc-manger curve. So I want to explain. Blanc-manger is a dessert, it's a traditional dessert in France, which is like that. So you see when you compare, you see it resembles. So it is why it is called the blanc-manger curve by some authors. Probably they are French authors and they wanted to make fun of it. I don't know. Okay. So this is the point. So I was extremely frustrated by this. I mean, so because I have this, I can benchmark stochastic gradient methods on these very simple functions. I mean, it is even in dimension 1. So of course, this is why where it is childish, because the objective of SGD is not to be accurate for the recovery of this kind of functions, but I don't care. So, but nevertheless, this benchmark show that, okay, the stochastic gradient descent are not able, if I use them just the standard way, to recover these things. Okay, so now I will explain a certain number of results which are elaboration or new results with respect to the Takagi formula and similar formulas, and where we will understand, I give you the main message immediately, that behind these series, there is a fixed point, contracting fixed point equation. Actually, the series is the solution of the contracting fixed point equation. And if we use it in the good way, then it is possible to implement SGD and to have sharp accuracy. Okay? And to start with starting initialization. There's no problem of initialization. So let me explain. So actually, it is an old piece of mathematics. What is interesting, I mean, so it has nothing to do, of course, with probability theory, of course, you observe, of course, and statistical theory, approaches. But nevertheless, it is an extremely interesting piece of mathematics, I feel. So once again, let's take this polynomial x minus x squared in this case. You can check this equation. So what j? I remind you that j is the hat function, and it is a function which is like that, defined in the interval 0, 1, and it goes from 0, 1 exactly to 0, 1, and you do things like that. Okay, and the peak is at 1. So it means that j is a function which is piecewise affine. And you can check this equation. H is equal to a certain given term, which is in this case j divided by 4, plus, and this is the important thing, 1/4 of h composed with j. Since j is a polynomial, it is an identity between on the left hand side it is a polynomial, and on the right hand side it is something which is piecewise polynomial of the same order, because h composed with j is clearly second order polynomials on the interval 0, 1/2 and 1/2, 1. And then once you have checked that, the series that I've shown is just the Neumann series of the equation. And why it is the Neumann series? Because the equation is contractive, because you have a coefficient 1/4. And this is the fundamental series. And so that now there is the possibility to use it and also to generalize it. First, I will show generalization, and then to use it to design an algorithm. Well, yes, it's perfect. So first, the generalization. Actually, it is possible to generalize to any polynomial, any monovariate, any polynomial of one variable under the following form. So the notation are standard for people who come from finite element theory and finite element approximation of PDEs. So first you need to define what are called basis functions. So the hat basis functions is there. So a little change of notation. I will use functions, basis function, which are like J or a fine per interval, but here in this case 4 intervals, 4 subintervals. Okay. So for example, in dash, dash, yes, dash, it is a hat function, but we will not use that function. Instead, we will use the blue functions, which are, for the simplicity of the math only, which are functions that are flat, affine somewhere, with a slope, non-zero slope, and then flat again. And they go from 0, 1 into 0, 1. And I call this subset of function EH. H refers to the number of, to the size of the intervals. So exactly H is here, 1 divided by 4. And as usual in numerical analysis, we have a tendency to look at what's going on when H tends to 0, it will be the case. Okay, so this set of functions is a subset of the previous ones. So the first result is the following. Take, I forgot to mention, take a polynomial H of any degree. So H is in P, is a polynomial of degree n, of one variable, Yeah, I forgot to write that, it's a mistake. So H is any polynomial, you take one polynomial. Question, is it possible to generalize the previous equation, functional equation, and under the following form? Find E0, which is a function in VH. Find EI, which are function in EH, which are what I call basis functions, such that you recognize here the composition of H, the composition of EI with H, and find certain coefficients, beta I, so that you have this formula, an exact formula, exact, with the contraction condition that K, capital K, is the sum of the beta I, and it is contractive. And it seems strange, but actually this is extremely simple. If you think that H is a polynomial, these guys are either constant per interval or affine with a constant slope per interval. So H composed with EI is just a polynomial in X of the same degree than H. So here you have a linear combination of polynomials, interval by interval. And if ever you have enough polynomial, and if they are linearly independent, you can always find these guys. And this is but the point is that if you have enough intervals, and if you take a certain number of basis functions per interval, I do not desire to comment on that, then you can always be sure that the contractive constant is less than 1. An example. If you take X3, you can check, it is an example, it is that H is equal to that with E0, where is E0? Yeah, given, okay, so you have these formulas. And here it is the case where H is equal to 1/2, 1 again. And here the constant is 1 divided by 8, plus 1 divided by 8, plus 1 divided by 4. So it is divided by 1 divided by 2, so it is less than 1. So it is a generalization of what I said. So the point is the following, is that now, because it is composition, if you write the Neumann series, the fixed point method, which is clearly converging, there's no choice, it is basic math. So this guy is a function, it is the null function. So I initialize with the null function, and then okay, it means that for a certain H, I have to know first what is E0 and the beta I and the EA, okay? And then I can assemble that by and then the solution at rank K. So I forgot to say that, of course, K, what is K? K is the iteration number here, but if you interpret in terms of neural network function, it is the number of layers. K the number of layers. This is the point. So you have a function which have more and more layers, and they converge to the target with a rate that you control completely. Perfect. So actually, okay. So before it was the curves that we seen before, and we made some tests implemented in TensorFlow, but with exact initialization of the weights. I know it was in Julia, but it is the same. So, and we check that the accuracy is the one predicted by the formula, but unfortunately, it is still not gradient descent. Why? Because now there is a progress. The progress is that for any polynomial, I can implement this series where I have to know first the theoretical coefficients. So it's still the same problem that we have. But now I have the convergence. Okay. So now let's reformulate completely, and it will be the comment say the point of my presentation where I will use SGD. Now let's reformulate completely the algorithm. I want to use SGD. So I want to learn certain coefficients. So I decide that some of the basis function E1 until ER are decided in advance. And since they are basis function and I know how to, so I know that if I use enough intervals, so I am free to implement with enough interval and enough function per interval, the condition of the theorem are met. So I can somehow take randomly, it's not random, but the basis function. So the basis, these ones, they are taken at random. And assume that we were able to calculate a function fk at step k. The question now is to do the linear combination to get the beta I and to get the function E naught. But instead of using the theoretical value, because now I decide to learn these coefficients, I said, okay, let's assemble this function where the alpha I and the D naught are, it is a function, but you can parameterize with finite elements, no problem. So it is linear with respect to the coefficients in D naught. So it is linear with respect to D naught and alpha. Alpha is the collection of all the alpha I. And let's use this cost function. So the cost function, it is the L infinity norm between this function where the degrees of freedom are D0 and D naught and alpha and H. So this function you can assemble in a SGD code because it is just, you just have to change the cost function. It's no more the L2 norm, but the L infinity norm. And if ever I do oversampling, I can on my interval 0, 1, I can calculate this cost function. So this is what I do. So this is the cost function. And why the L infinity norm? Because it is the one which is adaptive to the contractive nature of the formulas. And now this is the algorithm. Initialize the function with 0. And the next step, optimize with SGD. So this is called argmin, but in practice, it is SGD that will calculate this coefficient. And then you can make a code for that. It is very, of course, very simple code, okay, for a very basic function, but nevertheless. So in terms of learning, it is called supervised learning because I know H, I know capital H, and I'm looking for the coefficients that reproduce H. Do this step, the calculation of the argmin with the SGD, and the next function will be this one. And then it is a loop. And then you loop. Okay? So any time of any step of the algorithm, you do SGD. And now the properties, summary of the properties is here. Yeah. You start with a function which is 0. So you need, say, 1 layer or 0 layer to implement that. And then because you do one composition, you need one more layer, the next step. Okay, so iteration by iteration, you increase the number of layers of the function, your neural network function. The minimization function is convex. So I do SGD to minimize this convex function. It is not strictly convex, but it is convex. It has always a solution. I take it. In general, it is non-unique, but I don't care. We don't care about that. So here we use SGD to do this minimization. So, but it means that at first step, I do SGD to minimize the convex function, convex cost function. At second step, another SGD to minimize another convex function. So the structure of the algorithm is really nice. Instead of using SGD to minimize one highly non-convex function, I use SGD to minimize a series of convex problems. Much better. So I avoid the minimization of non-convex function. But okay. And the theorem is that, okay, you have just to reproduce the proof. I will not do the proof. It is a good classroom exercise. You just have to make them. Okay. So the implementation. So now the question is it possible that this method can be implemented? I said that many times, but now let me give the details. So I use the SGD algorithm of implemented in TensorFlow Keras. I use the Adam method for the as the SGD. The cost function, as I said, is implemented with a custom loss function. Essentially, it means that I'm doing a supervised learning, okay? But for this completely academic problem, because H is a polynomial, of course. And technically, you can assemble, you can make a concatenation of layer technique to okay. Now I have an algorithm where I have the global algorithm, which are the loop iteration with respect to K, and the internal iteration. The internal iteration is the SGD, actually. And this is very classical when you have many loops, an algorithm with external loops and internal loops. I mean, to balance the accuracy that you ask for the inner loops with respect to the outer loops. So this is classical. And also, you can ask to the SGD. So it is called the learning rate. Yeah, the learning rate. One iteration after one global iteration. I mean K after the other. I diminish the learning rate. There is this is also classical in for okay. And and everything is perfect. I mean, for the basic function that I've shown, typically x squared. So you see, in terms of sampling, is completely stupid, of course, because I oversampled the interval 0, 1. So it's crazy. It's just I didn't want to look at that, so I decided to do oversampling. So it's almost continuous in X, actually. But nevertheless, the algorithms are clearly the SGD algorithms. And I follow the prescriptions, classical one. So they are batch, all these things. So here are the numerical results. At first iteration, so the objective function is x minus x squared. This is the curve that you see. At first iteration, I get a ReLU function, which is close to the hat function, which is close to x minus y, and then I iterate. So, and you see the convergence. You see the convergence because here it is closer and closer. And finally, after 4 iterations, you do not see the difference anymore. And you can calculate the errors, and the errors clearly they goes to 0. And not only they goes to 0, but you can get super small errors, which is, I know, a childish objective for stochastic methods, but I don't care. But the contraction number, you can check, it is really the 1/4 predicted by the theory, so that's good. So here, in this case, I managed to use SGD in a completely converging manner. And just to show you, there are other, for example, this is another polynomial. So here I took 9 intervals. This polynomial is of degree 5. And after a certain number of iterations, this is the errors, it is converging. This is, okay, this is another polynomial. So okay, so I have 15 minutes left, I see. So I will make a certain number of comments, and perhaps I will stop if there are questions. Probably it is Andre, but perhaps it is what I should do. Okay. So okay. So for me it was a success. Of course, once again, you can smile because it is for a stupid function, of course, and I am smiling too, of course. So now a certain number of questions. The problem is that this algorithm, even if I am satisfied that I have convergence, and the observed convergence follows the theoretical prediction. The question is still the complexity. When I have an algorithm, of course, the complexity. So the complexity is the relation cost versus accuracy. And especially here in the deep limit where I have k large. K is the number of layers, of hidden layers. Okay, and at every, okay, so if, okay, so the good point. If the cost, you measure the cost with respect to either the number of lines that you need to implement the iterations, or the time that you need to do the training, then it is super good because then for example, the time to do the training, it is the same time, one iteration after the other, because you have the same number of degrees of freedom to optimize at every iteration. So it is proportional to k. If you stop at step k, you have to, the cost is a certain unitary cost per iteration c, then multiplied by the number of iterations. And because you have the, yeah, and because, and clearly this is the logarithm, k is the logarithm of k to the power k. Okay, you have to put absolute values, and k is the contraction number. And once again, and this is the accuracy. So once again, we get the log of epsilon cost, scale cost of the Jarodsky theorem, which so it is excellent. But unfortunately, there is another hidden cost in this algorithm. It is due to the fact that when I have a certain number of neurons per layer, and that in this iterative structure, I mean the number, the number of calculation that I need to do, that the computer needs to do to calculate the function, actually scales more like d to the power k. You really have to be in front of your computer to see it, but I work hard to reduce that. And in this case, clearly, it's not absolutely not what you observe. So in practice, this is the second formula, which is the bottleneck. Okay, there are a certain number of theoretical problems, okay, which are important, which are interesting for this kind of approach, which to get optimal contraction constant, to optimize the basic function, and of course, then and the last point, of course, is perhaps more serious. I mean, so here I am able to do supervised training in a convergent manner, but for an academic problem. So the question is it possible to generalize to real life problem? For example, it is extremely tempting to try to generalize the following. No, it's not that. If it would be possible to generalize the following statement, it would be incredible. I mean, to replace one SGD for the optimization of a non-convex function with a series of SGD to minimize a series of convex functions, because it is what is done here in this algorithm. So if I could do that for general function, so it means for a real life problem, but of course I cannot do, you can imagine. it would be nice. So my feeling is that if there is a solution to this problem, it would be the solution would be first to generalize the functional equation for real life function. Oh yeah, this is good. So the explanation of this formula comes from that. If you have say 4 neurons from this layer and you iterate the structure I've shown, somehow the function of at the next layer, the next iteration, I mean the number of neurons per layer somehow, I mean the one when you really calculate, it's something like that. So you have a certain growth of okay. Perhaps okay, so I propose to stop the presentation because clearly the main message, I mean the message that corresponds exactly to what was the title, is now given. So I propose, André, that I stop the presentation and I can answer question. Is it okay for you? Is it good?
Of course. Thank you for the talk. Is there any questions from the audience?
Okay. So I know that this is a completely different approach with respect to what is. So I of course I look at the program, and so there's no computational statistic at all in my talk. It is the opposite. I want to control this part.
Thank you very much for talk. Alexander is here.
Yeah.
Can you make a forecast in which direction this development will go next 2-3 years? So which mathematical classes of functions will be considered?
Thank you very much. Thank you. Okay, so I show this slide. Okay, I can think of 2 different axes of research. No, I can think of 3 different axes of research. The first axis is, okay, it helps me to understand SGD and I can use it for real life project. I will not comment on that. This is separate, okay? Perhaps let me comment only on this point. I am really fascinated, honestly, by the fact that these once I get a certain equation, functional equation like that for a certain polynomial, okay, let's this one, the simplest one for x squared, then it gives me the possibility to write the solution as a fast convergent series, and it gives me the possibility to implement with SGD in a way that I completely control the errors. So I am fascinated by that. So clearly, mathematically, I think a good question, mathematically, is to ask for what function can we have such structure, such functional structures. Perhaps, okay, of course, if I use something which are different from polynomials, I will have probably remainders, extra terms, as small as possible, I expect. Okay, so because once I have the equation, everything, the solution is immediate. It is just an application of standard math for the solution of contractive equation with fixed point methods. Okay, so exactly that. So the SGD in my case, I control it only because I am able to write the problem as a fixed point equation. So the question is to generalize the fixed point equation. So this is I think it is the most interesting or fascinating for me problem. So I can show you one solution that I was very and in the same direction. You can ask yourself, is it possible to do it in 2D or for multivariate polynomial or for function or more than variable, f of x, y, z, blah, blah, blah. Okay? The real problem, of course, being of a function of, say, x1 until xm variables, because I am in dimension m. So, okay, so I'm not able to do, of course, to answer for general problem, but okay, so here it is a solution in the case of the polynomial of 2 variables, xy, and I was lucky enough to find this crazy generalization of the Takagi formula. I call it the Takagi formula. So this is the point. So for this, for example, you can check. Okay, so no, it's not. I do not have time to give the details, but okay. For one, there is one polynomial of two variables for which I was able to generalize the formula. So for me, the question is open, and it is possible that there could be a solution. So
I'm sorry, I interrupt you.
Yeah,
I just realized that this function x times epsilon is separable function. So your variable perfect variable. Is it
okay.
chance here?
Okay, I completely forgot. No, do not forget. But for example, in the Jaroski paper, he used the fact that it is separable many times. It is actually a key tool in his theorem by using what is called the polarization function. For example, xy, you can say that xy is x plus y to the square divided by 4 minus x minus y to the square divided by 4. So there are many ways to to use exactly what you say, the separation of variable type. But here it is different because it is really a transformation. Okay, it is different. So okay, so anyhow, I'm not able to give a precise answer to your question, but my main fundamental axis of research would be to generalize the fixed point equation for general function.
Thank you very much.
If I am able to do that, I can immediately implement SGD in a convergent manner. Actually,
thank you. Sorry.
Yeah. Yes.
Are there any more questions from the audience?
Sorry, it's again just I wanted to ask you, maybe you have some experience. Do you see some similarities between neural networks and tensor calculus, tensor arithmetic?
Oh, thank you very much. No, with neural network. Yeah. Oh la la. I completely forgot to say that. But when you write series like that, actually it is super close to, actually it is even the same as what is called residual neural network, RNN. Residual neural network have exactly that kind of structure. Why? Because in a residual neural network, what you do,
Yeah, this is exactly tensor format what I see in the middle. So
yeah, residual, actually, you implement more the difference between two iterates. And this formula, of course, you can also implement using the idea of residual. So actually, this structure is very close to RNN, residual neural network. Because more and more in a neural network community, people, yes, they work with the increment of the coefficients. So this kind of iterative formulas, you see it everywhere now. So it's not exactly the answer to your question, I'm afraid.
not really.
It's difficult because we are.
Any more questions?
I'm sorry, but I explained why. Look, you approximate one-dimensional easy functions. Then in 1D, then you can take tensor product with orthogonal function and d-dimensional tensor. So you have multivariate function which is d-dimensional.
Absolutely, but this is the basis of the Jaroski theorem, which is approximation theorem for multidimensional function. Okay, of course, you're right. I agree with you.
Oh, thank you.
I can do that, but I am more interested by finding solution to these funny equations directly for multidimensional function. But you're right, there is a way to pass from one-dimensional function to multidimensional function by tensorization, of course. And it takes a key role in the proof of the Jaroski theorem.
Any more questions from the audience? Maybe from the people online?
Perhaps I have to stop the sharing.
Okay, then I think we can close this talk. Thank you very much, Professor Bruno.
Thank you, André.
Very nice talk.
To the organization committee.